Hello and welcome to my YouTube channel, The Intersection. This is Professor Muhammad Ali. Please, if you would like to receive any updates, try to subscribe to the channel so you can get the updates as I make them. Now, we have been looking at diagrams like those, and we have made some ourselves together in the first video. But I haven't mentioned the word that it's very important that I'm going to mention it now, that we're looking at a deterministic, should be an I somewhere here, deterministic finite automaton. Now, automaton is the singular of the word automata. Why it's called deterministic? Well, there's two reasons why. One is no state has, or you can say every state. Let's look at it this way: every state, so a Q3 state or Q1 or Q0, Q2. Every state has every possible output, okay, on it. So, and there's no two ones here, or no two zeros. Only one transitioning from Q3 to Q1, and one transitioning from Q1 to Q. Not one and another one, for example, like that. So every state has every possible output, and there is no repeat. Okay, so that's why it's called deterministic. The second reason why it's called deterministic is it has a finite number of states. So finite, there's 1, 2, 3, 4 states. So that's why I called a deterministic finite automaton, otherwise known as DFA. I know what's happening to my pencil. That's not as I want it to be. Let's change it a little bit. Okay, so it is DFA. Okay, so it's deterministic finite automaton or deterministic finite state automaton. But this is what it's known with. And so, how do we specify this DFA? Well, to do this, we have the formal definition. The formal definition of the finite automaton, and it is 5 tuples. Q, which is the finite states. Okay, in this case, Q, we can say Q is Q naught, Q1, Q2. They don't have to be in order, but I like to always write them in Q3. Okay, the sigma is the finite set called the alphabet, and in this case, sigma, in our example, 0 and 1. The transition function, which is denoted by delta, the Greek letter delta, is Q cross sigma, and the output a Q. And I will show you, we have seen it before, but I'll go over this with you in a minute. And then the Q naught, in this case the Q naught is the starting state, and that's the starting state. We always have to have that little arrow that I forgot. That's the starting state. So in this case, Q naught is an also member of the Q states. It's a member of this Q state, which is, here it is. So that's, in this case, it's the same as Q naught here. And then the final state, which is a subset of the Q, and you can see the final states, in this case 2. I have them always in part of the Q here. This is Q0, Q1, that's Q1, Q2, that's Q2. And so these are part of the, so the final states here in this case is Q1 and Q. Let me organize this for you a little bit, because you might get to ask to do this on your own in an exam or a quiz. So let me just clean this up, and let me just do it right here. Okay, so I got my pencil. I got the right. Okay, so you'll ask to formalize a graph like this. So the first thing is the Q. Okay, the Q is all the finite states. So you would say, we'll do it this way. Okay, here we go. Q is all the states. Q naught in this case, Q1, Q2, Q3. And you would ask to, what is the alphabet? The alphabet, 0 and 1. Okay, and then you'll ask I'll do the delta, the last thing, because it needs a space. What's the Q naught? This Q naught is part of, remember, member of the Q. Okay, in this case it's the set. We write them like a set, like so. And then what is the final state? In this example, we have two final states, Q1 and Q2. What's delta? Delta is the Q cross sigma. So Q2 transition on 1, Q2 transition on 0, Q3 transition on 1, Q1 transition 1. So we're gonna create the table that we have done before. Okay, and on the left side we will put the current states. The left side will put the current states. Current states that we are dealing with, Q naught. Where? There. Then Q1, Q2, and Q3. Okay, so that's my table. And on the top of the table here, or the table here, I will have the inputs, 0 and 1. So now we're going to go and again, if you want to, our book doesn't require it, but some books, they will have an asterisk on the final states. Okay, so on Q naught, and if you read a 0, what would happen? We'll go to Q1. If you are on Q naught and you read a 1, what happens? You go to Q2. If you are on Q1 and you read a 0, you go to Q naught. See, Q1, read a 0. Q1, read 1. Q1, read 1, you go to Q3. Okay, that's a Q3. Q2, and you read a 0, you go to Q3. Q2, reading this 0, you go to Q2. Q3. Q2, reading a 1, you go to Q naught. Q3, reading a 0, what do you say? Go to Q2. Q3, reading a 1, I heard somebody saying Q1. All right. So this is, it's called the transition functions, and we denote it by using the delta, the Greek letter delta. Let's now work some examples. Okay, here's example 1. Example 1, we need to construct a DFA machine accepts the string that ending with AB. I hope that everybody recognizes the alphabet. So the alphabet in this example is sigma A AB. And the language is, an example is AB, that's accepted. AAB is accepted. And BAB is also accepted. Okay, so anything that ends with AB is accepted. So how would we construct the DFA? Now we need to remember that the length is AB, so therefore we need 3 states. So here's starting state, Q0 or Q1. Let's do Q1 because I'm always using Q0. And then the next transition state is Q2, and then Q3. So if the machine reads an input of A, it goes to state Q2, and then instead of Q2 treats a B, then it goes to Q3, and now I have an AB, and that becomes my final state. Okay, now if the machine reads a B, it's gonna go, it stays here. If the machine reads an A in Q2, it will wait in this state. If the machine reads an A, remember we need A, anything that's ends with AB. So if the machine reads an A here, is going to come to this state. So now I have A, AB. AAB ends with AB. If the machine here reads AB, or the input is B, then we're going to come right here. Now we have B, A, B is accepted. B, A, I can have B, A, B is also accepted because as long as the ending is AB. Let's see another example. Now in this example we are constructing a DFA that accepts string starts with a 0. As long as the string starts with a 0, it will be accepted by this machine. So you know the alphabet is 0, 1. Okay, the language, any sequence of string as long as it starts with 0. So 0 is accepted. 0, 1 is accepted. 0, 1, 1 is accepted. 2 zeros is accepted. 4 zeros are accepted. 3, 0, 1, 1, 1, 1, 1, 1, 0 is accepted. So as long as you're starting with the 0, then the language will be accepted by this machine that we're designing. So let's see how we design it. Here's our starting state. Let's say it's Q0, and then our output is 0. I'm sorry, our input is 0. Input on the top of the edge, always input. Our input 0, or we read 0. Then we go to this state. Now that's starting with a 0, so that's accepted. So then this is our final state. Does it really matter what I get after the 0? No. I can loop create a loop and put 0, 1 here. It doesn't really matter what I get after the 0. So if I get a 0, accepted 0, and then I read another 1, it's okay. 0, 0, 1, 1, 0, and then I read 2 1s. That's okay, as long as I start with the 0. Now, what if my machine here, my first state, the first initial state, we read a 1? We can't just loop it in because we cannot accept it. Cannot start with a 1. So if we read a 1, we go to another state. Okay, this state, it's called, let's give them symbols here. This is Q1, this is a Q2. This Q3 now becomes a trap state. A trap state. And some books, they call it dead state. I have seen other books called garbage state. But the trap state means that whatever get trapped here will never go to the final state. So it doesn't really matter what I get after the 1, because if it doesn't start with a 0, it's not accepted anyway. So it gets trapped here. Now let's look at this example. In this example, we want to construct a DFA that accepts string of length 2. So anything less than 2 or more than 2 cannot be accepted by this machine, or otherwise it should be rejected. So, and of course we have to assume the alphabet. Let's just use 0, 1. So the alphabet is 0, 1, and then if you want to see what language can be accepted, here we go. We are accepting 0, 0. We're accepting 0, 1. We're accepting 1, 0. And we are accepting also 1, 1. So as long as the length is 2, is accepted. So if we start with Q1 or Q0, and then we read, doesn't matter what we read in this case, not like the previous example, we have to start with a 0. If we read a 0 or 1, 0 or 1, we go to the next state, Q2. And from Q2, if we read a 0 or 1, doesn't matter if they're in sequence or not, 0, 0, 0, 1, 1, 1, 1, 1 is also accepted. We go to our final state, which is a Q3. All right. Now, again, the condition is cannot be less than 2 or more than 2. So what happens if I get more inputs, 0 or 1, I go to this trap state. Trap state. In the trap state, everything gets trapped here. So if I get more, I can just make a loop, and they all get trapped here. They will never go to the final state. So this is a trap state or trap state or dead state. We can discuss that more in class if you wish. Let's look another example. Construct a DFA that does not accept a substring AABB. So 2 A's and then followed by 2 B's. Now, whenever you see something like this, you need to do it this way or simplify it this way. Whenever it says does not, make it does. All right, make it does, and then I'll show you how to switch it. So in this case, we need a string AABB. So the alphabet is A, AB. And we need that sequence. The language should have the sequence AABB. Doesn't matter what comes after. It doesn't matter what's before, but we have to have that sequence AAAB. So let's start. Here's our starting state. Let's call S1. Our starting state, let's say it reads an A, this A here. If it reads an A, we go to state 2. Okay. At state 1, if it reads a B, we need it later, but we just loop it now because we have to start with an A. At state 2, if it reads a B, now we reached here because of this A. We're starting with an A. So if we read a B, we can't leave it here because then we will have a B here. So if we read a B, we have to send it back to the beginning state. So if we read a B, it goes back to S1. Now, if we read in S2, if we read an A, we go to S3. Now we have AA. We have an A here and an A here. Okay, so now what happens if we, at this state, S3, okay, at this state S3, if we read an A, okay, if we read an A here, and the way that we reached here, we have AA. If we read another A here, we just loop it in. And then if we read a B, we go to S4 or state 4. So that's, if we now we got AA, B at S4, here. If we read an A, here, we will have, so far we have AA, B, AA, B, and if we read an A here, we will have an A in the middle. We can't have that because we need BB. I hope you are understanding what, okay, we can't have that. So we need to send this A back to this state. Back to state 2. Now, now if we read a B, if we read a B, we go to our final state, S5. We go to the final state, S5. Now, what happens if we read another A or B? It doesn't really matter because as long as we have the sequence AABB, what comes after them, they're no longer an issue. So this is for a does not. I mean, it does. This is for it does. Remember, we're simplifying it. Now, if we want to make it for it does not, now it becomes very simple. Make the non-accepting states to be final states. So we are going to remove the final state from S5 to we're gonna make the others our final states. So S1 will be our final state. So oops, I made a mistake here. Let's switch back and make it. We can redo. Yep. Okay, and let me just change the color. All right. And this becomes a final state. This is a final state. This is a final state. And this is a final state. And this is non-final state. That's for does not accept. In your book, there's multiple problems like those that says does not contain this substring, does not contain this substring. If whenever you see neither contain this or that, always simplify it by making the problem for what it does accept or it does contain, and then switch the final states. This is the final cut on this video, and I will make more for you, God willing. Thank you. Bye-bye.